Hello, my name is Corey Zhao, and today I'll be giving my 15-minute presentation on the CS final project, which is my topic is about recognizing people in cartoons. So, first, let's talk about the introduction. So, let's go over briefly a bunch of stuff. So, first, the problem. Well, what is the thing that we're doing here about cartoons? Well, first, many forms of deep learning models have been developed to classify and analyze images. So maybe not text form, maybe not audio, but for images. And there's a lot of different models for them, including various forms of convolutional neural networks, CNNs. These are the most popular. However, the field of cartoon characters is very niche. So although we may have a lot of data on, for example, real human beings or real reality items like objects in real life, we might not have as much experience or exploration on cartoon stuff. So this is going to be an example of applying a deep learning model on images in cartoons to do classification. So the data set, okay, so briefly, we're going to be using a data set from Kaggle, which is called the Marvel Heroes data set, and we'll go into it a bit more later. And it has like roughly 3,000-ish images that we will be using, and it has 8 characters, 8 different Marvel characters. And then for technology, okay, so the technology here mainly is going to be the computer science tool, which is going to be the CNN, the convolutional neural network. So the convolutional neural network is actually a pretty unique structure, which is why it's really popular for images. But there's 2 parts about it that are most important that I'll be going into a little bit in the next few slides. So the uses and benefits, well, I guess the uses and benefits are a little bit niche, but it's helpful to try and apply what we know about machine learning onto different cases, like onto different domains. Because, for example, if we haven't really tried doing image analysis thoroughly on cartoons, then it doesn't hurt to try. And also, I mean, I guess some specific use cases could be like, it could help better label online images. For example, maybe Netflix could use this, but it could also help with data collection or recommendations. And it could also help fight against maybe certain copyright issues, or maybe someone doesn't want to get spoilers, so they could have censorship and they could prevent leaks or something like that. Yeah, and then now drawbacks and challenges. Well, for cartoon characters, the advantage is that the advantage about this topic is that it's not been as well explored before. But that's also its drawback because it's not that popular. So there's not a lot of quality data sets that are well labeled and that are organized that are available online for us to use. And I ended up choosing one about the Marvel cartoon characters. So it is still cartoon, but the quality is a little bit of an issue, and it has a lack of systemic like data creation. So some of the images there are really weird. Like they might be about like Loki's horns, or might be about some meme or something. And I don't know why it's in there, but it just is in there. And I looked through a lot of other data sets as well, and they had similar issues where it's like it wasn't the best quality. So that's going to be its major drawback. So the working example, well, we'll see this again later, but the end of our example, end of our project, we had one example that had around like 85%-ish test accuracy. So it was pretty good. I would say it's really, really good, considering that our data is not the best. So I was very surprised about that, and I'm very happy. Now the conclusion is, okay, so it's basically a summary. Well, we're just implementing the CNN on trying to classify different cartoon characters. Great. So let's talk more about convolutional neural networks. So let's see. Convolutional networks, in the timeline of machine learning, from linear regressions to like decision trees and neural networks and other deep learning models, convolutional neural networks have been a staple method of interpreting image because of 2 things. So what is most commonly associated with convolutional neural networks? Well, there's the convolutional layer, which is where its name comes from, and also pooling layers. So these 2 main parts actually create a really powerful tool because first, the convolutional layers, they apply filters onto, if you imagine the image as like a bunch of pixels, they apply filters onto these pixels that take advantage of like the adjacency, where like they're not just random numbers, but they have a relationship to the numbers around them, to things around it. So we have like this kernel or this image that goes around, yeah, and we have experience with CNNs before. The second thing is that the pooling layer allows for the CNN to also not be location specific, because if you think about it, like an apple here is not that much different than an apple like shifted over here. Like it's still the same object, it represents the same thing. So there's no certain emphasis on like specific nodes having specific activation values, because it's just the relationship of the nodes relative to each other, but not a global location. So that's why we have a pooling layer that just kind of, usually it's like max pooling or average pooling, that kind of makes it not location specific. So that's why the convolutional networks are so good. And this is a deep learning model. And yeah, convolutional layers and pooling layers is good for image analysis and classification. So, but also here, the CNNs are an application of deep learning that uses a lot of computational power. So it requires a GPU that can really speed up a lot of the calculations, which is why for this project we did it in Google Colab, because Google Colab has these free access GPUs that we can use. And below we have a little image of convolutional neural networks where we have our input, convolution, and then the pooling. And then at the end we also have this fully connected neural network layer where it's like a dense layer that classifies the end result into our actual outputs. Great, so now let's talk about what specific convolutional neural network model we're going to be using in this project, or this project. So we're going to be using the MobileNet v2. So this is a pre-trained model. It's a CNN model. And what is it? Well, first, pre-trained models, well, we have data that we want to train CNN models on, but the data is not actually that big. It's only like 3,000-ish big. So what ends up happening is that overfitting is going to be a really big issue. So we can't actually efficiently train a large model and learn correctly because we don't have enough sample size. So something that tends to happen, especially for non-image cases, for non-cartoon cases, especially for like more real or more common objects, you would take a pre-trained model, like maybe ResNet 50 or something like that, that is already trained on this huge data set of images. So it already has the structure of the CNN model built in, and it has the weights already done. So instead of trying to build it from scratch, you already have this working CNN model, and you just need to fine tune it to your specific examples. So in this case, I chose the MobileNet v2, and it has, because it has this, it's built for object recognition. So I was thinking, oh yeah, this could probably help us classify faces and recognize the faces in cartoon characters. Yep, and yeah, so our individual data set isn't going to be enough, but we can add layers on top of it. So here I chose to freeze all of its weights. I didn't want to deal with any overfitting issues or any like data size issues. So I didn't want to touch any of the original MobileNet, which has like over like 2 million parameters, I think. So I just didn't touch that, and I added a top layer on top of it. So dense layers on top of it that we can manually fine tune to make this model closer fit to cartoons. And that makes a lot of sense. So it's like, okay, cartoons, we kind of don't have this exact like specific model for cartoons. So we're going to take its close cousin, which is a CNN for like maybe non-cartoons, and then we train it or adapt it to work for cartoons. Great. And then we see here that this is kind of how we use the MobileNet. We just use the tf.cares applications, and then we just like upload it, and we have this pre-trained model. And so we have some of the parameters here, and we have not trainable equals false, so we're not going to touch any of the original model. Great. And then there's a summary of it. Is really long, but the summary of it can be seen on the HTML file if you want. Great. So now let's talk about the data set. So the data set here is a data set from Kaggle, and it's called Marvel Heroes. And I think there's a link that's inside of the paper. It's inside of the abstract, and I think it's over here too. No, it's not over here. Yep. But the data set, yeah, it has 3,305 or 3,035 images of the characters, the 8 characters: Thanos, Hulk, Spider-Man, Doctor Strange, Loki, Captain America, Black Widow, and Iron Man. So these are, and then the dataset actually contained cartoon versions of these things. So it wasn't the actual actors or characters themselves. For example, it would be the cartoon version of Hulk, and the cartoon version of Spider-Man, and the cartoon version of Thanos, and the cartoon version of Captain America and Black Widow and Iron Man. So I also attached some images in the sample data set. So if you want to see what the cartoon images look like, there are some good images that I picked inside of the sample data set. Yep. And then, so how do we use this data set? Well, first, I mounted Google Drive to the Google Colab, and I went to Kaggle and I downloaded the dataset onto my local computer. Then I uploaded the zip file. I unzipped it and I uploaded the data onto Google Drive, and then I just upload it from Drive back to my Colab, basically. So yeah, and then so here it is. Here's the path in my Drive, and what happens is this data set is a little bit weird. It's not the best quality, so it's a little bit weird, but it has, it splits already into a train and a test, but there's no validation. So, and we don't know how they split it. So what I did was I just took all their data inside of their train and their test, and I just added it all into one big bunch, and then I split it later myself. So what I did was, okay, I just went through the directory of valid. Oh, they had a valid and they had a train. They had no test. Yeah. So I went through their valid, and their valid has 8 directories inside of the valid directory, and then inside of, for example, a Thanos directory was all the images of Thanos. So I just kind of went through and I took out every single image and I added it to this one large images array and labels array. And then now we just have, after this, I did the same thing for the training, and then I just had this 3,000 long images array and labels array. And we can see, yep, let's see. Yep. Okay, so now let's do some more coding. So I have this array with all my images and stuff. So what I did was I did train, test, validation, split, and I did it twice so that I split, I used like one of the methods and I just split it twice, and I got 70% train, 15% test, and 15% validation. And then now I need to do my data generator. So there's going to be a couple slides on this, but briefly, because we have MobileNet v2, there's actually an application from TensorFlow that has the preprocessed input for the MobileNet v2. So this is what the data gen for the test, train, and validation looked like originally. We actually did some changes on this that I'll talk about later. Great. But then to use our data generator, we actually have to change our train images, which is a one-dimensional array of pictures, and I changed it into a 4-dimensional and MP array. So I just used mp.stack, and then we can see that the shape is now 4-dimensional. Yep. And then when we created our labels, we just used the names, like for example Thanos or Spider-Man, but we don't want to actually use the strings, so we had to just arbitrarily assign the strings to a number and then just classify them categorically based on their numbers. So that's how it was working. Yep. And then here we define our train generators, and we use the 4D MP array, and then we use the integer version of the train labels. Yep, great. And now we finally use the pre-trained model. So the pre-trained model, we just upload it here, and it's false. And okay, so this is the bulk of our basic code. This is kind of the basic structure. So we have our pre-trained model, and we're not going to change it, but we're going to add layers on top of it. So we add dense layers, and output, and we have a final dense layer. So, and then we have here, we use the pre-trained model.output here. And we use softmax, ReLU, but there's no other really additional stuff on here. We use the optimizer atom, the loss is sparse categorical evaluation, and we just fit the model, and I used 10 epochs at first just to see what it looks like. And we used both our train generator and our validation generator. And if we look at the training, well, we see that it's clearly overfitting. So here we had nothing to combat overfitting here, and it's just overfitting. But an important thing to know is that throughout this entire project, overfitting was a very big issue. So we had to balance between high accuracy or overfitting. So like if we wanted the overall model to do really well in training or in anywhere, if we had high accuracy, then the validation was left behind and it was just stuck at 70, it was overfitting. But then if we stop overfitting, then the training and the validation, they don't overfit anymore, but they just both cannot go above 70. So it's very difficult for this model to learn effectively above 70. And we can see here the images, oh, it's just overfitting. So now we need to talk a little bit more about overfitting. So some of the causes of overfitting, well, it could be too complicated, the model could be too complicated, low sample size, poor data quality, or hyperfixation on little details, so just overtraining. And we want to solve that by using L2 regularization, dropout layers, and data augmentation. So I'll briefly go over the data augmentation is I had the data gen from earlier, but instead of just having the preprocessed input from MobileNet v2, I also added some rotations, some shifts, and some zooms and stuff like that. So we had some data generation, some data augmentation. So we have larger sample size, and these are some additional results. So on the left here, we see that this actually looks pretty good. It's not as overfitting as the last one. The one on the right is still overfitting, but let's look at the one on the left. So the one on the left, we have 2 dropout layers, and we have 2 L2 regularizers. But the one on the left actually has 100 epochs and no data augmentation. And on the one on the right has data augmentations, but I only have 1 dropout layer and I only have 1 L2 regularizer. So we kind of see, I tried out a lot of different combinations as well, so not just this, but I can't show it all here, but we had a lot of issues. But if you look, like the data is really not going above 70, the validation. Because if you look here, well, this scale is actually off because it's by 0.02. So this is really not overfitting at all. But you see that both the train and the validation, they barely exit 0.72. And here, when it does overfit, we see that, okay, the validation still doesn't exit, but I can make the training go higher. But it's just not working. So the final result, I did a lot of testing, a lot of tweaking. And what I found as a balance was, first, for the data augmentation, I got rid of this rotation. I didn't want to augment my data too much. I got rid of the rotation, I made the shifting smaller, and I didn't allow for horizontal flips. And then I have 1 dropout layer, and I have 1 kernel regularizer. But this kernel regularizer, I don't know if you can see, is actually by 0.04. So it's not 0.05 anymore. So I made the kernel regularizer a little smaller. I do have a little bit of data augmentation, and I have 1 dropout layer, and I also have only 40 epochs. And then if I run the evaluation on the test, I actually get an 85% accuracy, which is really, really good. So in this model, it pays off that we have no overfitting. Because we have no overfitting, the test data set actually has very high accuracy. So that's a very, very good thing. Yeah, and then I'll attach my YouTube links at the slide after this. Thank you. So this is my video.